series for characterization at UBC. And today we will hear from Dr. Eva Nichols. She is an assistant professor in the UBC Department of Chemistry. She's also a Tier 2 Canada Research Chair in Molecular and Interfacial Electrocatalysts. And she will talk today about attenuated total reflectance surface enhanced infrared absorption spectroscopy. Thankfully, that has an acronym. And so she will talk about building a molecular picture, ATR-SEIRAS, as a window into electrode interfaces under operating conditions. So thank you very much for joining us. And we're looking forward to learn more about this technique.
Thank you very much. Okay, I'm just gonna, I see the clock isn't really clocking, so I'm gonna set a timer here. All right. Okay, great. Well, thanks everyone for being here. It's my pleasure to join you today. I'm actually the first one of these seminars that I was in town for and could attend, but I've joined remotely in the meantime. So as was mentioned, today I'm going to tell you about this technique that's quite interesting to me that we have in my lab here at UBC, and I'll abbreviate that mouthful as ATR-SEIRAS, or just SEIRAS for short. That's much more convenient. So my goal today is to share with you a little bit about the background, about why this technique is amenable, what you can use it for, how it works, and some practical details. And then towards the back end of the talk, I'll share with you some stories that I've been a part of to understand adsorbate behavior under applied potentials, and also a couple of case studies from the literature that I think illustrate the potential of this technique. Oh yeah, that thing has stopped again. Want me to wave at it? Hello. Okay. All right, let's see. Okay, so let's dive right in. So my primary motivation in trying to understand this, oh, sorry, do you think we can move the screen sharing thing? Thank you. My primary motivation in this space is to focus on ways to electrify chemical conversion. And so I'm sure many of the audience members here are interested in a similar topic. Essentially, this would involve taking our intermittent and localized renewable energy sources, renewable electricity, and using this to power devices like electrolyzers that can convert, in this illustrated example, carbon dioxide into liquid fuels or other valuable chemical products. But if you think about how these devices would work, uh-oh, now something's not advancing. Okay, I promise we'll get this working at some point. If you look inside these devices, you'll realize quickly that we need some electrocatalysts to help us along here. And so there's been a huge amount of study by numerous groups across many disciplines to try to identify good catalysts, meaning cheap, meaning abundant materials, meaning high activity, so fast kinetics, low overpotentials, and selective for the desired product. So there's a lot that goes into this. And a really important question that comes alongside is, how are these catalysts actually operating? How are they degrading? How do their behaviors change as a function of either applied potential or time on stream? Or essentially, we want to know, what are these materials doing under operating conditions? So in a really generalized sense, my group is interested in sustainable electrocatalysis. We're interested to take an oxidized feedstock and couple it with a number of protons, represented here by N protons, and another number of electrons, using an electrocatalyst to make value-added products. And there's a huge number of reactions you could envision here, everything from this relatively simple proton reduction to make hydrogen, all the way to more complicated CO2 reduction or nitrogen reduction to make ammonia fertilizers, making CN bonds from a combination of CO2 and urea, or oxygen reduction to water. But all of these steps are multi-step redox processes. They require more than one electron and more than one proton. And as a result, they often have really high kinetic barriers for these reactions. So my group and many other groups around the world are interested in understanding how can we optimize this and how can we selectively design catalysts that work better. So just since some of you are unfamiliar, I thought I would introduce my general research program here. So this is what we do in the Nichols group down in the chemistry department. I'm a molecular chemist by training and an electrochemist. And so we spent a lot of our time designing molecular model catalysts where we can position certain groups that are redox active or proton relaying groups like this one here in really well designed and thought out positions, and understand how kinetics, for example, of CO2 reduction that might happen at this iron center are dependent on electronics of these molecules and the placement of various proton donating or relaying groups. So we spend a lot of our time sort of focused on these model systems that are homogeneous, dissolved in electrolyte. Many of these cases work in organic electrode chemical conditions, but we can get a lot of really high fidelity mechanistic information from this. Alongside, we're also interested in polycrystalline metal surfaces and modifying electrodes in a fashion like this, where we could tether some kind of chemical group to the surface and use that interaction now between this, what I'm abbreviating L here, and a molecule of interest that's an adsorbed species on the surface. For example, here, adsorbed CO2. So as you can probably imagine, we're really interested in the fundamental chemistry, the reaction mechanisms, how these proceed. And we're also really interested in characterizing catalysts under operating conditions. So that's where the technique that I'm going to talk about today comes in, ATR-SEIRAS. Before I go too much further, I want to just allude to the fact that there's a lot going on an electrode surface, and I think many of you probably appreciate that. But I wanted to draw a sort of interesting parallel, which is from biology, actually. So this is the enzyme active site of a really important enzyme that's involved in carbon dioxide fixation. So this is CO2 bound here. This is actually a crystal structure where you can see the carbon of CO2 interacting with this Nichols center of this very interesting and complicated cubane-like cofactor in the active site of the enzyme, and an iron atom out here. And there's also these lysine and histidine amino acids that form the peripheral environment that help via hydrogen bonding for CO2 to access this bent shape. Okay, and so it's now widely understood that these lysine and histidine residues allow this bending of CO2 to take place more easily, and ultimately the CO bond to cleave to make carbon monoxide. Okay, so the takeaway here is that in enzymes, these really ornate biological machines are designed with a particular focus on tailoring the local chemical environment. And a similar thing can be thought of at an electrode interface. So there's a nice perspective on this in Nature Catalysis by Erwin Reisner's group, where they illustrate different ways that this could happen. So you could put some sort of functional group, append it to the surface, and now it can undergo interactions with CO2 in a fashion that's somewhat reminiscent of what this enzyme might do. Okay, and so there's been a lot of thought put into, how might you engineer an electrode surface, for example, putting cages on the surface or trying to tailor certain solvent or ion interactions with adsorbates here. But largely, we're still sort of in a regime where the electrode interface does what it wants and we sort of have to respond, right? So it'd be great to understand a little bit more about willful design of these interfaces so that we can perturb them at will. Okay, so in my group, we are interested in self-assembled monolayers and how they may interact with electrochemical systems for catalysis. So this is just a generic scheme showing the myriad of ways that a self-assembled monolayer, or a SAM for short, could interact with a surface and could change, for example, local concentrations of CO2. This is all sort of illustrated in the context of CO2 reduction, but you could extend this to whatever your reaction is of interest. Okay, and particularly this one here, where an adsorbate L here can change the either destabilize or stabilize a relevant intermediate in the catalytic cycle. But these are nice diagrams to draw? How do we actually know chemically what's happening at the interface? And so this becomes a bit of a tricky challenge, given a few details that I'll share with you soon. Okay, so I'm going to be speaking about an infrared spectroscopy technique today, and so I just wanted to give a really brief overview and review for those who are unfamiliar with how infrared spectroscopy works. So traditionally, we think about this maybe in a transmission type format where you have some broadband IR light source. And here are going to be just illustrating the different frequencies of this light source, okay? Then you have a sample, which for example, in this illustrated case is just water. And then some of these frequencies are going to be absorbed by the sample so that you do not see them at the detector, okay? And so the detector, of course, is just recording the absence of some of these frequencies that were absorbed by the sample. And because those frequencies correspond to excited vibrations in the sample, we now have a really nice and high fidelity fingerprint for what molecule is present or what functional groups are present in this sample. So there's a lot of different modes that you could use to do IR spectroscopy. So there's that very sort of basic transmission approach. There's also attenuated total reflectance. I imagine many people here have done that. This is really common nowadays. So here you have a high index ATR crystal. Usually this is silicon or germanium. And you put your sample on top. This could be a powder, a solid, a liquid. And a small evanescent wave is going to penetrate out of this ATR crystal and via interactions with the sample allow you to get the same sort of information here at your detector. There's also reflection absorption or specular reflection and diffuse reflection. I'm not going to talk so much about these. As you can tell in the name of the technique, we're going to be speaking about attenuated total reflectance or ATR mode. Okay, so IR is a really powerful tool to understand these electrochemical systems. And specifically for understanding molecular changes, for example, to speciation or the local environment. You could think about sample speciation. Is your adsorbate protonated or is it deprotonated? That would matter in a lot of cases. For a local environment change, how much hydrogen bonding is there? Are we changing the solvation? Are we changing the orientation of the solvent near the electrode? So that's what I mean by local environment. Okay, but how do we record IR spectra during operation of an electrochemical cell? So it turns out that this is not so easy, particularly in aqueous systems or other systems where you might have really strong IR absorbance. So think about water. Well, water is a very strong absorber of IR radiation. And so if you're thinking about passing a beam through an aqueous sample, you essentially just swamp out all of your absorbance is going to exciting water, right? So there's really not much signal to be collected at the back end. And so we need a sort of crafty way to remove the contributions for strongly absorbing solvents. We also have to think about how to include an electrode in all of this if we want to study a system under applied potentials. And if we're trying to think about measuring adsorbates, chemical adsorbates on a surface, we're thinking about monolayer coverage or below that, right? And so actually seeing something visibly for one monolayer of molecules on a surface can be really challenging. So this is sort of a nice summary, I think, of the challenges we're up against. Here's how we deal with them. So there are two main setups that you could use or modes for doing spectroelectrochemistry, FTIR spectroelectrochemistry. So basically merging electrochemistry where you have some sort of electrode surface either here or here, you can apply your potential, and then a way to probe the system using IR. So the first is external reflection. This maybe is what you would think about doing if you didn't have a better idea as your first go at it. You take some sort of IR transparent window, for example, calcium fluoride, and you just smush your working electrode up against that window. So here is the working electrode. This could be I don't know, a glassy carbon surface or some kind of polycrystalline metal or a single crystal of metal, okay? And then here's your bulk electrolyte. You have a counter electrode and the reference electrode, and off you go. And the challenge here for doing external reflection is that your IR beam has to actually come out into the electrolyte and reflect off of your working electrode before going to the detector. But you're going through what looks in this diagram to be a fairly thin distance of electrolyte, but it's actually still fairly significant. You can often lose a lot of signal by doing this, and you have a lot of, let's say there's water in here, so we run into that solvent absorption problem again. A different way of doing this is using internal reflection. And so this is the ATR idea here, where just like before, you would have your sort of standard ATR configuration here. Think of this as being silicon or germanium crystal, okay? So we're gonna have an evanescent wave that can penetrate out of the top of this ATR element. But now you could coat the top of the ATR element with a material that would be your electrode. Okay, and so in this particular example, let's consider this to be a thin gold film. Then if the evanescent wave is able to permeate outside of that gold film, you could begin detecting molecules that are bound to the surface. Okay, but what's really a great benefit of this second configuration is that now you can have as much bulk electrolyte up at the top here as you need without sort of having your IR beam to go through all of it and reflect back. Okay, so this internal reflection configuration is vastly preferred for that. Okay, and so here's just a brief summary of the sort of drawbacks and positive aspects here. I would say in this second internal reflection configuration, there is a bit of a constraint in terms of the identity of your working electrode. It has to be something that you can deposit on top of your ATR element, okay? And so, for example, single crystal gold surfaces or other metal surfaces don't work in this configuration. That would be strictly external reflection. But for the vast majority of materials, we are able to do internal reflection. Okay, so now this brings us to the ATR sort of internal reflection, but now adding one extra layer in here, which is this surface enhanced infrared absorption spectroscopy, or SEIRAS. So we're going to use that internal reflection approach and add a little bit of spice to it. And that's going to be the surface enhancement. This is now going to solve one of our next problems, which is how do we actually see monolayer or submonolayer coverages? Remember, that's really challenging to do. So this is a cross-section of an electrochemical cell that we would use. So here's going to be the IR source, ATR crystal and detector, and this is illustrating a schematic here of the evanescent wave. So we're going to deposit a really thin layer here of in this case, gold. That's what's illustrated, nice and yellow, but any material that would be amenable. And we're going to now take advantage of the fact that SEIRAS is surface sensitive, meaning that we're going to be selectively probing signals that come from molecules that are absorbed at the surface rather than existing just near the surface in solution. It's not perfect, so you absolutely still can see some signatures from molecules that are not actually absorbed to the electrode, but you have much better enhancement of molecules that are actually chemisorbed. Okay, I'll talk about a little bit more detail in a second. Okay, but this is great now because we can perform experiments in solvents that are very strongly absorbing, and we can essentially cut out a lot of that noise from all of the solvent above if we're looking at larger enhancements from molecules that are specifically absorbed. Now, the enhancement is about 10 to 1,000-fold enhancement in signal compared to a molecule that is not absorbed to, or that is not being measured using ATR-SEIRAS. And so this actually is good enough to see submonolayer coverages. In our group, roughly you can see maybe like 1/10 of a monolayer. Something below that, it may be more challenging. Of course, this also depends on the strength of the dipole. Okay, there's also a really important selection rule here, which is that we're selectively looking at modes that are normal to the surface or perpendicular, or we're looking at their normal component. Okay, and so one can actually get some orientation information from molecular adsorbates, and I'll show you examples of that in a little while. Okay, so all this is to say that ATR-SEIRAS gives us chemical information about adsorbates on the surface. So one of the pioneers of this technique was Masatoshi Osawa. And so he's written a lot of really nice papers that kind of highlight the basics and the fundamentals of this technique. I just wanted to highlight a couple of these here for you. So what they're doing here is, this is work back in the 90s on nanoparticulate silver. And they're recording either just powder form of this molecule. I believe this is para-nitrobenzoic acid. This is recorded just on calcium fluoride windows. So you see here the IR signatures of that molecule. Okay, and then they start looking at deposition of this molecule on top of these nanoparticulate silver surfaces. So here, this number here is going to tell you the size of the nanoparticle of silver, okay? And so same loading of the nitrobenzoic acid. But you can see that if you have no silver present, you see absolutely nothing for really small loading of the molecule, right? And that's what you'd expect. Everyone intuitively knows you have to put enough material on your ATR in order to see a signal, right? So if it's really, really low coverage on a surface, we're not going to see a signal. But as soon as we start having larger and larger nanoparticles, you start to see really enhanced signals. So this is the signal enhancement aspect, but not too large, because now you peak and you sort of decay in terms of signal. Okay, so I wanted to also draw your attention to the fact that the relative intensities are very different in these SEIRAS spectra down at the bottom compared to just a para-nitrobenzoic acid that has no orientation specificity. So here you can see actually it's this 1690 wave number peak that's highest, okay, most intense. However, on a surface, it's the 1350 wave number peak that's most intense, okay? And so that's telling us that there's an orientation specificity for this molecule when it binds to the surface. So we can actually get quite detailed information here if you understand your system well enough and you know what you're looking for. Okay, now why does this happen? So here's a nice plot showing the, well, this is percent transmittance here from different silver nanoparticles. And so you can see the smallest nanoparticles, 4 nanometer diameter, have this really sharp feature, and then essentially flat as we go out to larger wave lengths or lower wave numbers. Okay, sorry, this is going from the UV into, UV visible into the IR here. Okay, and then as we increase the size, you'll see that there's this like really large, broad feature here. Okay, and so this is coming into play as a really important aspect for ATR-SEIRAS. Essentially, what we're going to do is we're going to take advantage of this large absorbance feature on the silver nanoparticles or other metal nanoparticles. Okay, and we're going to get localized surface plasmons that can become in resonance with the incident IR beam. And so this now generates surface plasmon polaritons at our dielectric boundary between the particle surface and the electrolyte. Okay, so these oscillations are going to polarize the particle, and they're going to lead to really large local electric fields. That's sort of what's being depicted here, okay? So locally, or in this nice picture from Wikipedia, as you bring two, let's say, high aspect ratio nanoparticles together, they can sort of almost touch. Right in here, they kind of kiss each other a little bit. And in the middle, there's going to be a very high local electric field, which can really help polarize your adsorbed molecule. So we're essentially taking advantage of this very high local electric field to enhance the IR absorbent aspects of that molecule. Additionally, just the fact of chemisorption, so the molecule as it adsorbs to a surface also dramatically polarizes the molecule. So essentially there's sort of two different explanations here for why we're getting this really large surface enhancement. It's local electric fields, yes, but it's also chemisorption, where the molecule now attaches chemically to the surface. Okay. And this helps explain why you can still get some signal enhancement for, let's say, for electrolyte or solvent molecules that are near the interface, but not chemically bound to the surface. Okay, so to summarize that, I said that the signal enhancement in SEIRAS is actually largest for chemisorbed molecules. You can see some enhancement for physisorbed molecules, although it's less. And the biggest important aspect here is polarization of your substrate. Now, what do you actually need for SEIRAS? So you need a roughened surface. I think this is very much agreed upon. So think of high aspect ratio, sort of like spikes or little nano daggers on the surface, that's best. Having a very pristine, really smooth, extra clean surface is terrible for SEIRAS. And my group routinely encounters this problem that it's actually really tricky to make the correctly prepared film. And I'm happy to talk at length about this in the Q&A if people have questions. But this is a very much understated aspect of SEIRAS, the difficulty in making the correctly prepared film and making it in a reproducible way, and in making it in such a way that it actually survives for the duration of your experiment, particularly in cases where you're evolving gas, like hydrogen or CO bubbles. Okay, another supposed requirement for SEIRAS is that you have a plasmonic metal surface, although recent work has been sort of extending the boundaries of what we can perform SEIRAS, what surfaces we can perform SEIRAS experiments on, and I'll show you a little bit about that in a moment. And you also need generally chemisorption to the surface. Okay, so here's a picture just to get everyone sort of familiar with what we have in my lab. So we have this really nice Bruker Vertex 80 IR instrument. This has a liquid nitrogen cooled detector. That's important for SEIRAS for the sensitivity of the detector. We are looking at small signals after all. And we also have this variable angle of incidence accessory here from Pike that allows you to control the angle of the incident IR beam. Okay, so you can optimize for signal that way. Okay, additionally, we have this accessory at the top, which is an electrochemical cell. This is from Jackfish SEC. It's a Canadian company, actually. I'll show you a little bit more about them in a second. But essentially, it's buried inside this variable angle accessory is our silicon ATR crystal. And on top, this piece sort of bolted on top via an O-ring is the electrochemical cell. So you can put all of your counter and reference electrodes in here, fill it up with any electrolyte you want, and or customize the rest of this aspect at will. Okay, so this would be the path of the IR beam from the source to the detector inside your instrument. Okay, and that's just the cross section to orient you to what I've shown before. So how do you prepare this thin gold film? That's a great and thorny question. So the way we currently do it in my group is using argon sputter coating. So here you can see a picture inside our argon sputter coater, and this is the silicon crystal after sputter coating, and here's an SEM of the surface. Now this technique used to work really well for me, and it doesn't work well for us anymore. So this is what I meant by there's some challenges here in film preparation, and again, I'm happy to talk more in detail if people have questions. Okay, I wanted to also highlight a couple of newer possibilities. So these are things that my group is sort of interested in, but we haven't quite started working with. And there's this really nice company in Germany called iRubis that offers micro-machined silicon chips with waveguides. So you can see them here. And so this now, it's just your sort of standard thickness of silicon wafer, allows you to go away from that big, hefty silicon single crystal. And these, I think, are roughly $100 per chip. So not super cheap, but you could treat them as disposable if you were well-funded, I guess. The previous silicon crystal I was showing you is multiple thousands of dollars. So that one, definitely not disposable. So what's nice about this is that these chips now allow you multiple sort of passes of your IR light through the chip. And we can now sort of decrease the size, giving you rise to this nice little chip. That means that we can start coating these with materials that are perhaps difficult to remove off of silicon, very strongly adhering. It's hard to clean these, and so you can essentially make an electrode and use it until it's no longer good and then throw it away. So there are a lot of really innovative and exciting developments in this area, and many of them are led by Ian Burgess, who's a colleague in Alberta. So you can see here, for example, that they coat these silicon wafers with indium tin oxide, and then, for example, here with gold, or in this example on the left with palladium. These interfaces are a little bit better than direct metal onto silicon, which often have really poor adhesion. And there's additional developments in this space that I'm not mentioning here that I'm also happy to talk about. Okay. Also, Jackfish SEC, which is a company that Ian Burgess began, sort of a spin out, offers a wide variety of electrochemical add-ons that you could tailor here, so flow cells or other cells as well to add. Okay, so now I'd like to dive into some examples of using this ATR-SEIRAS technique and information that we can gain from these types of experiments. So the first example I'd like to highlight is one that I worked on in collaboration with a postdoc here, Dr. Muriel Delay. She's now at the University of Basel. And this is work that I was involved in as a postdoc at Yale University. So we were curious about how the acidity of adsorbates, of molecular adsorbates, would change with applied potential, and whether we could correlate that with a measurement of the electric field at the interface of an electrode. Okay, so this work is published. Here's the citation. And just really briefly, I want to sort of show you this cartoon schematic of a self-assembled monolayer on an electrode to explain what we might expect. Okay, so if you think about here is a, let's say, metal electrode. Here we're illustrating silver. And then you have some kind of self-assembled monolayer that has an acidic functional group. So think of like a long chain alkyl thiol with a carboxylic acid terminus. So this terminus could be either protonated in the carboxylic acid form or deprotonated as a carboxylate. And you might think, okay, well, let's write out an equilibrium model of the surface here. And we're not going to go into all the derivatization here, but we can define a term here, pK1/2. This is like a pKa, but it's the solution pH at which half of your molecules on the surface are protonated and half are deprotonated. And that should depend on the potential here in a sort of Nernstian relationship. Okay, so here's this familiar term for electrochemists, 2.3 RT. So we expect that for every change in the applied potential or experienced potential, we should see a change of 1 unit in pKa, 59 millivolts. Okay. So we were curious to see whether that would actually pan out with a molecular adsorbate where you have, sorry, let me go back for a second, where you have this large drop in applied potential through the organic piece of your self-assembled monolayer. So what we did, here again is a silicon ATR element coated with gold. And then on the surface, we're making a mixed self-assembled monolayer. So we're going to have some kind of protic molecule. Here we're using mercaptobenzoic acid. So the mercapto piece, sulfur, is to tether this molecule to a gold surface. And then here's the carboxylic acid portion that we're going to study protonation changes. Also, we're going to have an electric field probe. This is mercaptobenzonitrile. The purpose of this molecule is that we can hopefully correlate changes in protonation state of the molecule of interest with a measurement of local electric field. And I'll explain that in a bit later. Okay, and all of these experiments are going to be done in aqueous electrolyte. The reason I'm drawing OD here is because we're using deuterated water, D2O. The reason for that is because the bending mode of water, this delta mode of water, perfectly overlaps where all the signal of interests are for the carbonyl and the asymmetric carboxylate stretch. Okay, so let me just orient you to what we're looking at. So we have these mixed self-assembled monolayers, and first things first, we're just going to look at their SEIRAS spectra, which is what this is, as a function of PD, or PD because it's in deuterated water. Okay, so in pink, this is the most acidic, PD of 2. And you can see a large sort of broad feature here around 1700. You see these really sharp features here. These are ring breathing modes in the sort of 15 to 1600 wave number range. And then there's nothing present here right around 1400. Okay, and then as you increase the PD, so make it more basic, this large sort of broad feature eventually decays, and we see a large increase in this 1400 wave number feature. Okay, and so based on this and some literature precedent, we're able to assign the feature around 1700 to the carbonyl stretch of the protonated species, and this large feature around 1400 to the symmetric stretch of the carboxylate. Okay, these are just showing you that you can collect some really beautiful PD-dependent spectra, and now ATR-SEIRAS spectra. And actually, for each color representing each different PD, we can now start applying different potentials. Okay, and so essentially, that's what's sort of overlaid here. That's why you see some peaks are going up and some are going down. These are different spectra now with reference to a defined standard. Yes. Okay, so that's what I wanted to show you here is how the spectra of your ATR-SEIRAS change as a function of applied potential. Okay, so here you can see that as we apply more positive potentials than our reference point, we see a bleach in the carboxylic acid features and an increase in the carboxylate features. And similarly, if you apply more negative potentials than the reference potential, you see a growth in the protonated species and a bleach in the deprotonated. And so we believe that this is nice evidence showing that there is a potential dependent protonation and deprotonation change. We're also able to generate these sort of sigmoidal plots here, where you can correlate the fraction of protonated carboxylic acid and deprotonated carboxylate. And this looks very much like a titration curve, right? So from these data, you can actually measure the intersection point, or where both of them are essentially at 50%. It's not perfect, but decently close. You can look for 50% carboxylic acid, 50% carboxylate, and figure out at what PD that occurs. Okay, and that now will give you access to that parameter pK1/2, the solution PD at which half your surface is protonated and half is deprotonated. I also wanted to mention this nitrile probe. So we could look at this one as a measure of local electric field. And this depends on something called the Stark effect. The Stark effect is essentially saying that if you take a dipole like the nitrile CN stretch here, it's going to be polarized delta plus to the carbon side and delta minus to the nitrogen. If you now put this in an electric field, you're either going to stabilize or destabilize this dipole, right? And so the wave number will shift, the vibrational frequency of that dipole will shift as you stabilize or destabilize this dipole. Okay, and so you can see that here. So this is these are SEIRAS spectra of the nitrile on our gold film, and you can see that the maximum wave number actually shifts as you go from positive applied potentials in red to more negative ones in purple. Okay, so there's a shift to lower wave numbers here, consistent with the fact that we're stabilizing this nitrile dipole. Another interesting feature here is that the relative size of this peak is growing, and that's explained by essentially a reorientation of the molecule on the surface. This is a really clean and classic example of that fact. So as you go from more positive applied potentials to more negative applied potentials, this molecule is actually standing more upright. And so more of this nitrile stretch becomes normal to the surface. So we went through a whole sort of detailed analysis of this system, and I won't bore you with the details, but suffice it to say that we see some really different concentration effects in terms of effective acidity, or pK1/2. This red line is that expectation of our 59 millivolt per decade change. And in light blue and dark blue, this is our observation, either in less concentrated electrolyte or more concentrated electrolyte. So you see the expectation is very different from the prediction. In this case, the way we understand it is that there's a huge drop in potential as you go across this SAM interface, okay? And so the applied potential may be expected to be changing acidity by 59 millivolt per decade relationship, but the experienced potential of where this carboxylic acid group is massively attenuated, okay? And essentially we believe that ion penetration, ion pairing, and solvation at this interface is dramatically screening what this carboxylic acid is experiencing, even at the sort of molecular length scale away from the electrode. Okay, I also wanted to briefly mention some work that we did to understand cation identity. So we followed up, this is a sort of tag on a set of experiments to the same mixed SAM, but now looking at variation in the electrolyte composition. All the previous work I showed you was in potassium phosphate. Here we're looking at lithium, sodium, ammonium, and tetrabutyl ammonium phosphate buffers. Okay. And so here's just a nice little schematic to show you changes in the hydrated and dehydrated radii of these cations. So to try to understand the role of ion pairing and maybe SAM penetration of these cations, and whether there might be a trend with either the size of the hydrated or dehydrated radius, we again turned to SEIRAS. So here you can see these are, again, ATR-SEIRAS spectra of the mixed SAM in the presence of different electrolytes. And so recalling that this wide feature around 1700 is illustrative of the carboxylic acid, the protonated form. Okay, and this peak here is reporting on the deprotonated form. You can actually right away see that with tetrabutyl ammonium, this is maybe the most clear trend here, that the SAM is dramatically less acidic. Okay, and these are illustrated at PD7. Many of the other cations are roughly comparable, looking at the relative integrations of these peaks. Another interesting feature is that the peak maximum shifts quite a bit depending on cation identity. And so this goes to show that the cations are actually specifically interacting with the carboxylates at the surface. So you can see that, for example, the tetrabutyl ammonium trace here in black actually has two different maxima, suggesting that there's two separate identities for the carboxylate species on the surface. The lithium example is really broad. That's this purple trace here. So that's maybe suggesting a large number of different carboxylate interactions between lithium cations, and possibly also the role of water solvation here. Okay, looking at the nitrile, because remember it's a mixed SAM, so we have sort of two different visions on this surface. You can see again that tetrabutyl ammonium is sort of an outlier, and really all the rest of them behave in a very similar way. So here are the stark responses. This is actually showing you how, as a function of applied potential, the wave number changes. So the slope here and the sort of y-intercept is reflective of the local electric field, or at least it scales with the local field. And based on this difference for tetrabutyl ammonium, you can see that actually the tetrabutyl ammonium cation is not really able to penetrate as well into the self-assembled monolayer. And so we're seeing larger local electric fields with that cation specifically. Okay, so some takeaways from this set of studies is that especially with the larger tetrabutyl ammonium cation, we can see less ion pairing with the SAM carboxylates. And I think it's interesting and illustrative to, sort of bring in your intuition here. This really greasy, bulky cation, yes, it's going to be less Lewis acidic, and so it makes sense that the carboxylate or the carboxylic acid in its presence is also going to become less acidic. And we also saw less SAM penetration of these cations with the larger sort of bulky and greasier tetrabutyl ammonium cation. So what I hope I've been able to share with you from those several examples is the fact that here we've been able to look at deprotonation equilibria and also interfacial electric fields and get sort of complementary perspectives on a fairly complicated electrolyte interface. Okay, in the time that's remaining, I wanted to just take an opportunity to share with you a couple of really quick examples that I think might be of interest to you as well. The first one is something that my group thinks about quite a lot. This is now classic work from Osawa and coworkers. It's been more recently dramatically popularized by a whole host of other groups. And that is the notion of interfacial water reorientation or solvent reorientation in general. So you can actually see this if you take, I think these are recorded on a platinum surface or possibly gold. Sorry, my bad, I forget which one, but I think possibly gold. In sulfuric acid. And so you can see these dramatically different water features as a function of applied potential. So here it's more negative applied potential going towards the top and back, more positive applied potential. See, with respect to a reference potential around 0 volts versus RHE, you see these dramatic changes in both the OH stretch and the OH bend, which is right here. Okay, so how do we explain this? Well, the explanation comes from the fact that the water molecules, you think about, these are not eyeballs, these are water molecules, the 2 H's in black and the O in white. There's actually a reorientation that's potential dependent. So at potentials sort of out here more close to, let's see, more positive. The oxygen of water is actually, oh, sorry, no, this is more negative. I'm confusing myself on this axis. More negative applied potentials, you have sort of the water sitting in a horizontal location. So the hydrogens are sort of almost flat with the surface. And then as you polarize your electrode to more positive potentials, the water molecule actually spins around. So now you have the delta minus of the oxygen pointing more directly towards the surface. Okay, and so these changes in solvent orientation can actually be measured spectroscopically. So that helps kind of paint a more fuller picture of what solvent specific changes might be happening. And lastly, I wanted to share with you what I think is a really nice study by Feng Zhao and Bingjun Xu in the context of CO2 reduction. So this is a gold electrode now that they're looking at for CO2 reduction to make carbon monoxide. And so, of course, carbon monoxide has a beautiful IR signal. You can see this here showing around 2100 wave numbers. This is adsorbed CO. Okay, but interestingly, if you apply really positive potentials, you see no CO, and if you apply really negative potentials, you also see no CO. So it's just in this tiny little region here of applied potential where you can actually record a signal. So our explanation for this is that, well, from CO2, you obviously need to generate CO, so we need to be applying reducing potentials. But the negative potential loss of CO is essentially just exclusion and displacement by solvent and cations. Okay, so this is actually a bit of a complication because you can't just apply the potential where you want to generate CO and hope to see it on the electrode, right? Because it's gone. And so this required actually a little bit of a crafty trick. So they use a square wave pulse where they apply a negative potential to generate CO from CO2 and then collect the spectrum at a different applied potential and sort of just toggle between these two. So you can see an example of this here where we don't need to be applying just a fixed potential, but rather you can jump back and forth. So this negative applied potential is where they generate the CO and then measure at 0.4. And now you can see these really beautiful ATR-SEIRAS spectra. So having employed this nice little clever pulse trick, they were able to study, it's a long story, but a really good one. So I recommend this paper if you're interested in this. There's a whole host of isotopic labeling experiments and mass spectrometry coupled with ATR-SEIRAS experiments to look at spectroscopy of the interface. And really this is pointing at the fact that there's a really fast equilibrium exchange between bicarbonate and CO2, where the soluble bicarbonate acts as a source locally of CO2 that can be reduced at this interface. Okay, and so with that, I hope I've achieved some goals here of sharing with you the utility of ATR-SEIRAS to learn about molecular changes in adsorbate speciation or intermediates in electrochemical transformations, and hopefully left you with an interest in SEIRAS. So with that, I'm happy to take any questions, and thanks again for your attention.